So again, if you are able to steal hashed passwords, and if the passwords are weak, there isn't really much that we can do to prevent the attacker from guessing those passwords. But what we can try to do is to make the attackers work slower, to need more time. And to do that is we're going to use salt. So the idea is that we want the attacker time to be d times n. We don't want the attacker time to be this plus n. Okay, because if it's d times n, then in the case of LinkedIn, n is 6 million, and d is 2 to the 20. So if, let's say, a scan of d takes you an hour, then an hour times 6 million, it would be 6 million hours. That's a lot, right? So ideally, we want the attackers to do work in d times n. So we want to prevent the amortized attack that works in d plus n. Okay? So to prevent this amortized attack, what happens is that the server is going to salt each hash. What that is that the server chooses a random salt, and then it hashes the password with the salt. Okay? So when Alice wants to log in and provide her password, the attacker is going to look up Alice's profile, is going to see what salt, the server is going to look up Alice's profile, is going to see what salt the server used for Alice, and then is going to hash the password Alice applies with the salt and see whether it matches the stored hash value. So this is how Alice authenticates pretty much as before, with the addition that the server is hashing the salt in addition to the password. Okay? And the salt, again, is stored inside Alice's profile on the server. So, but here's what happens. The server is going to use a different salt for two different users. So two equal passwords from different users have different hashes now. So the dictionary attack is possible, but you need to do a dictionary attack for every hash now. You can't just do one dictionary building for for all the hashes. You have to do one dictionary pass for every single hash of a password. Why? Because the salts are different from one password to another. So the attacker will need time d times n instead of d plus n, so it can no longer do this amortized time. And this is much, much slower, because if n is 6 million, then it's 6 million times slower for the attacker to reverse the passwords than it was without the salts. So here's a concrete example. So let's say that the server has this database of usernames and their hashed passwords. For Alice, it has some certain salt, and then it has the hash of her password and the salt. For Bob, it has another salt, and then the hash of Bob's password and the salt. Now, let's say the attacker stole this database, and now wants to crack the passwords, wants to figure out what is Alice's and Bob's password. So, let's say he tries to first guess Alice's password. He's going to compute a table for every single word in that dictionary and compute the hash hashed with Alice's salt. If there's going to be any match between these hashes and Alice, then the attacker knows it found Alice's password. But note that this table is useless for Bob, because this table is with Alice's salt, not with Bob's salt. So the attacker now has to construct this table again for Bob, and then again for Chris, and again for Eve. So it takes time d, the size of the dictionary, times n, the number of users, which is much slower than d plus n. Is this clear? Any question? Okay, so that's why today servers store salted passwords. Okay, salted, hashed passwords. And there's another way to make the job of the attacker even slower. Can anyone see it? Use a slower hash function, exactly. So again, because the attacker has to build this dictionary of hashes, it would be ideal if the hash function takes a while to compute. So in order to use a slow hash, what you can do is you can, when you hash a value x, you hash it, 100 times. Because then it's 100 times slower. And I mean, this is nice because if, let's say, it took 3 days for the attacker to mount the attack, if it's 1,000 times slower, then it's going to take 3 years or more than that. Yeah. A good point. That's a very, very good point. So the point is exactly that it's also going to make Alice's login process slower, right? Because when Alice logs in, the server has to compute that hash for her to check that her password matches, the hash, the slow hash of her password and hash. Okay, so now if Alice was logging in, let's say the check-in process was 1 microsecond, or let's say 1 millisecond, now 1,000 times slower is going to take a second for her. Maybe that's still okay. Your login process will be a second instead of 1 millisecond. As long as it's not super observable for a user, maybe that's okay. But the point is that with the attacker, it's going to take 1,000 times longer. Also, but it's 1,000 times, 3 days or 3 months, so it really can take it from something barely feasible to something very infeasible. Okay, so there's a tension there, but it could still be useful, to use a slow hash function within what doesn't really bother a user. All right, so the main takeaways from hashing passwords are that you should never store the passwords in clear text. You should store them with hashed, with salts, and with slower hash functions.